University of California, San Diego. Henry Abarbanel, who is a distinguished professor of physics and also a research scientist at Scripps. And he graduated from Princeton a long time ago in physics, and even longer than me. Since I remember Henry, I always associate him with complex dynamical systems, forecasting of nonlinear systems. Even in the early days, even the very early days that people were not interested in that stuff, and that the data was not of interest in data simulations and so on. That's what, and I'm glad I received recently a paper from him on using machine learning, reservoir computing to forecast using time series, and he will talk to us about today. I invite him to talk to us about today, and he's very kindly agreed to it. So Henry, anytime you want to start, we're ready.
Okay.
And thanks for taking the time.
Thank you for the introduction. Let me share the screen. Okay. Good afternoon. So this is what I'm going to talk about. And I would like you to especially note the along with at the bottom, 3 of my PhD students in physics, Randall Clark, Jason Platt, and Adrian Wong. And this work was done together with Steve Penny, who is at University of Colorado in Boulder and has been working on this subject and its applications to weather prediction, numerical weather prediction. I'm going to talk about slightly smaller models than numerical weather prediction, but in principle, there's an opportunity there. So, whoops.
Henry,
Okay.
do you want to put it in a presentation mode, or?
I can. I didn't. Let me try. Ah, that's better. Okay. Okay, so I'm going to talk about reservoir computing. So let me set the stage by saying what a reservoir is. It was defined approximately 20 years ago by several people. Herbert Jaeger, Wolfgang Maas were certainly the 2 earliest people.
Sorry, Henry, to interrupt you, but I see a double screen. I don't know about others.
Oh, I can only see this one.
Do you see anybody else? Eric, do you see?
There is a double screen, yes.
Yeah, it's the presenter screen.
It's the presenter mode.
That's okay, yeah.
Not the slide.
I see a mixed slides as well.
Yeah, it's the presenter screen, so.
Should I go back to the smaller?
I think you can fix it by going up to the top there where it says display settings.
Yeah, but I think this is fine. I mean, maybe we can just.
However you want to do it. Yeah, I've had this happen to me too in Zoom. So.
Okay. All right. Sorry. So, so a reservoir is a recurrent neural network, which is a fancy name for a dynamical system. And this network has random connections among the active units at its nodes. And I'm going to talk about reservoirs with N of about 500 to 5,000 nodes. The network is defined by an adjacency matrix, which is N by N. And I must say I was not very interested in this until recently because I couldn't figure out why a random matrix could be useful for learning anything and predicting the future inputs to it. But my students got really interested in it. The talk today is really to clarify the question and bring some of the experience that I and other people have had in doing this. So there's a collection of physical, I don't know really of any biological systems that have been used as reservoirs. So there's a 2019 review by a Japanese group in neural networks, and they talk about lasers, they talk about electric circuits. My favorite reservoir turns out to be a bucket of water, which is kind of a reservoir in itself. So if you're interested in the applications, this may be a very good place to start. There is also a set of papers, primarily from the group of Brian Hunt and Ed Ott at the University of Maryland. I recommend them to you. They apply the method, but not so much the background for the method, to many, many different problems, small ones and large ones. Okay, here's the idea. Oh, can you see my cursor?
Yes, we can.
Oh, okay. So the notion is the following. Here's the definition of a reservoir. It has state variables R, and that's the n-dimensional reservoir. It has a vector field, depends on R, and depends on some input. The input, which generally is called U of t, is d-dimensional, and the reservoir variables are n-dimensional. The key in what I'm going to say depends on what's called generalized synchronization. There are conditions, which I will tell you how to find for a given problem, which give a relationship of the input as a function of time equals some function phi, or which is a vector also in d-dimensional space, of the reservoir variables. It's called generalized synchronization. It has been around since, I don't know, 25 years ago. And if that occurs, and I'll tell you the conditions under which it does, if it occurs, then you can train the parameters in this unknown function by minimizing, in a least square sense anyway, there may be better ways to do it, the difference between the input and your representation of the function. Once you've done that, you take a problem which is not autonomous because it has an external input. You use the phi that you determine in some way or another and put it into the differential equation for the reservoir. It now becomes an autonomous equation in R, and the information on the input is encoded in the function phi because it's been adjusted in this way. I didn't ask, but if you have any questions, please, I'm totally comfortable with your interrupting and asking questions. So this really is a slight enlargement of what we're talking about. So we have a vector in n dimensions for the reservoir and a vector in d dimensions for the input. And we need to relate an n-dimensional system to a d-dimensional system through this generalized synchronization. The criteria we're going to use are properties of the adjacency matrix, in particular, its largest eigenvalue, which is also called the spectral radius, the probability of non-zero connections, because the connections are typically sparse, and the magnitude of the input signal. We will look at the capability to have generalized synchronization as a function of these variables. There may be others, but these seem to be sufficient as far as we can tell. Okay, I'm going to talk about generalized synchronization. It may be completely known to you. It may be completely unknown to you. I'll try to rectify the latter situation in a gentle sort of way. So generalized synchronization is, again, in general, never mind reservoirs or anything else, the case where you have a state variable with its own vector field, and that vector field is d-dimensional, while you have an input which has no differential equation. So it's an input from data or from an external force, and I'm going to give that k-dimensional variables. If d equals k, we can have what is probably familiar to do with identical synchronization, namely x equal y. But if d is not equal k, so you have two different dimensional systems, we can still have generalized synchronization, which relates the k-dimensional state variable or input variable to a function of the state variable. All right, here are some things we do not know. I do not know. I don't think they're known. If the function phi, about which we have, frankly, very little analytic information, or quantitative, I should say, the function's phi, of course, is invertible. We can invert it to a function of y equals x of t. This is now a vector in d dimensions relating to a vector in k dimensions. We don't even know if phi is differentiable, but we are going to proceed assuming it is. So again, here's the general case, not autonomous. When you have generalized synchronization in this form, it becomes an autonomous equation, and you can solve for the future of the input, and I'll show you how that goes, by solving this autonomous differential equation. To say it again, all the information about the input is not lost, it's embedded in this functional relationship. So we're going to have to do what we can to understand something about that. Okay. Going to build a reservoir, namely a recurrent neural network. You have to put some sort of active units at the nodes. I'm going to first talk about putting at the nodes of the network a two-dimensional system which is widely used in computational neuroscience, that was invented in the early 1960s by Fitzhugh and Nagumo in separate publications. And it involves an equation for a voltage and an equation for an auxiliary variable, which doesn't have an immediate biophysical interpretation, but from the point of view of a differential equation, it's fine. Alpha runs from 1 to n, and the index A runs from 1 to D. So there's an input driving current that drives the voltage equation, and that has in it a matrix of dimension n by d. And there is also now the adjacency matrix that connects the voltages at location beta to the location alpha. And the W equation doesn't have any adjacency matrix. You could put one in there, I guess, but it's not necessary. And it satisfies this differential equation. And just to be precise, A and tau, a time constant, and B are just numbers that are used in a standard fashion. The only thing that in some sense relates it back to timescales that are appropriate to the neurobiology are the fact that this is measured in milliseconds. And I0 of V is simply sigmoid, which turns from negative to positive if you start with large negative V around V sub P. I don't know why we're calling it that. It should be turning point or something. And C is just a width of the, this corresponds to the slope of the hyperbolic tangent. All right, so why this equation for what you put at the reservoir nodes? I think after a few more slides, you're going to agree it's completely up to you what you put at the reservoir nodes. The question really is whether or not that reservoir synchronizes with an input signal, in which case I hope to explain that you can do good forecasts under those circumstances. So I'm going to start off with a reservoir of 1,000 nodes. So that's 2 times 500 of these differential equations at the nodes. The input that I am going to present to this reservoir is going to come from a driving force, which is taken from the Lorentz 1963 system, and it goes into a reservoir with hyperbolic tangents or Fitzhugh-Nagumo neurons at the nodes. So here's the first calculation, and I will explain the input to this. In both of these pictures, for the same reservoir and input setup, we have 2 different ways of determining the regions of generalized synchronization and the regions of non-generalized synchronization. The blue area is non-generalized synchronization, and the red is synchronization, generalized synchronization. One method calculates the conditional Lyapunov exponents of the reservoir. I call them conditional because they depend on the function phi, and more precisely depend upon the input. The simple, but calculating all these conditional Lyapunov exponents can be done, but it's a long and not very revealing computation anymore. But the easier way to do it is called the auxiliary method. And I'm going to explain the auxiliary method to you. And again, if you have any questions as I go along, let's take them.
Henry, I have a question here on the, we only have 2 colors. It looks like there's shaded.
I'm going to show you a 3-dimensional version of this, and you'll
Okay.
see that there's a very steep slope at the boundaries between.
Okay.
I have no idea, by the way, whether that line in white is fractal or not, but in 3 dimensions, it looks like a very steep slope.
Yeah.
All right, good question. And you'll notice that what I've plotted here is a 2-dimensional projection using 2 of the variables I talked about, the spectral radius and the density of connections. So we see if we take the density of connections at about 2%, and we take the spectral radius anywhere in this region from small to large, we will have generalized synchronization. And I didn't put together a graph of what happens when you don't have generalized synchronization, but I'll comment on that later. Okay, here is what's called the auxiliary method. And the idea is to make identical replica receiving systems. So here's reservoir A, and here's reservoir B with the same input and the same vector field. And you can probably make a theorem out of this, but you can anticipate that for large enough times after the initial condition, the coordinates of x sub A and x sub B will be the same, even though the initial conditions are not the same. So the transients and the way that these 2 dynamical systems, recurrent neural networks, if you like, actually get together, you can test by evaluating any function you like. I guess it better be smooth, but why would, anyway, Again, I don't know the criteria for these functions, but we can plot this function called chi for reservoir A and reservoir B, or receiving dynamical system A or dynamical system B. And then we plot this function on reservoir A against function on reservoir B, and we expect to get a straight line at 45 degrees. The generalized synchronization, as I have said, depends upon the parameters in the adjacency matrix, and could be any parameters that are in fact in the vector field for the underlying reservoir or differential equation. Again, we have examined these three: the spectral radius, the probability of non-zero connections, and the strength of the input. So these ideas were formulated in the middle 90s, and in 1998 was the first experimental confirmation of this idea of generalized synchronization. A very nice paper from a group at University of Queensland in Brisbane, Australia, published this paper, which is interesting to read. They essentially modulated an ammonia laser by a CO2 laser. And the intensity signals here are the time series of them. I don't know which one is which. Maybe it says in this teeny tiny print. I couldn't get it to be much bigger. And they examine the importance of the strength of one input versus another. These two time series are, even to the eye, dissimilar, and they come from different dynamical systems. They cleverly avoided the use of a replica reservoir by saying the time scale for these systems taken together is, in their case, 150 microseconds. So they took the intensity of one of them and plotted against the intensity at t minus delta tau later, which delta tau was 150 milliseconds. And they show several graphs with different values for delta t and different intensity values. This is the one that shows generalized synchronization. There isn't much more to say. They demonstrated it experimentally. It's been demonstrated in lots of other systems. The one I must say that most surprised me was this paper explaining how generalized synchronization is used in breaking cryptographic systems. If that's of interest to you, this is kind of a review article. It's 15 years old, but I couldn't find anything newer. Okay, what about other reservoirs? A very useful reservoir is known as the hyperbolic tangent reservoir. So this is the differential equation for the state variable of the reservoir and the input from whatever input system you have chosen. Again, the Greek indices run from 1 to n. The Latin indices run from 1 to d. It's a very simple thing. The reservoir is damped. The nonlinearity is the sigmoid called the hyperbolic tangent. And that's it. This will play, the simplicity of this will play a role when I come to my discussion of why we're doing this. But let's get to that. Okay, I thought this example would appeal to you. So we took the shallow water equations and the paper by Sodurni from 1975 on how you solve the shallow water equations efficiently and accurately. Here are the equations. They're probably well known to you. There are 3 dynamical variables for these equations. One is the velocity in the east-west direction, the velocity in the north-south direction, and the height of the surface of the shallow water field over X and Y. Also, the potential vorticity is used here. It's a very nice, convenient additional variable that summarizes some of the symmetries that are involved in the shallow water equations. I'm probably singing to the choir to say that shallow water equations form the core of the computations that are done in global climate models, but I'm not going to go into that. That would take a little bit more computational sophistication than we brought to the problem so far. Okay, here's George, here's your picture. Okay, so this is the error between reservoir 1 and reservoir 2. When that error goes to a very small number, there's generalized synchronization. And when that error is a very large number, there's no generalized synchronization. This was done for 1,000 hyperbolic tangents, and the dimension of the system was very small, but large enough to be interesting, I think. They took the shallow water equations, the PDEs, put them on an 8x8 grid. You have 3 variables, the 2-dimensional velocities and the height. So this is a 192-dimensional problem, actually somewhat larger than we have tackled otherwise. And so the question is, if you choose your spectral radius and your strength of the input in the purple region, how well can you do to predict data from the solving the shallow water equations? And that's what I'm going to show you. So the input are the data from the shallow water equations. We're in this region. That input is called U of T. The reservoir is 1,000-dimensional. The input is 192-dimensional. And this is a hyperbolic tangent reservoir. So here's an example of the prediction. This time in hours after the training period, which we'll look at in other cases, looks like this. I mean, you can see for yourself that it does very well at the beginning, it departs later, and eventually fails. There's several things that one can think to do. One is to try to guarantee that the solutions to the shallow water equations are regular, not chaotic. If they're chaotic, this would simply be the result of the intrinsic instabilities associated with a chaotic system. If not, there are a number of things you can do numerically, including just taking smaller time steps. And along with the height, we calculated the vertical vorticity by the usual formula. You can see that that also does pretty well for the predictions. It starts to miss here, and it follows here that the predictions last no longer in this case than order of 4 hours if you're an optimist. Okay, I'm going to move on to other applications. One of the other classes of application not covered in the earlier literature.
Henry, can I just ask a question here?
Sure.
Because somehow using a very sparse grid in finite differences, that also affects the, so I was wondering how the resolution would come in from the finite difference solution. Could that affect the accuracy and the long time integration?
I'm sure the answer is yes. I don't have any demonstration. This is frankly where we just ran out of computing resources. We'll beg and borrow them from elsewhere to answer your question, because the calculations, once you've done them on an 8x8 grid, which is indeed very sparse, can also be done on 1024 by 1024.
Yeah, or you can change to, because when you have these propagation problems, and this Oliger showed that a long time ago, right? As you increase the order of the scheme, finite difference, and so on, you the phase errors or whatever errors you have in time, you attenuate them. So, for example, if I use a Fourier method here for my training and
Right.
so on, and then you're in the coefficient space, that would be also extend the time. So the question is, because I'm interested in this type of things, how you can extend the valid prediction time, right? That I think Ott and some other people from MIT define as a metric in another paper using reservoir computing. So I was wondering if it was an artifact, how much of this is an artifact of your discretization versus another.
Well, I can only say that we did not examine that.
Yeah, yeah. No, it's
Can it be done? For sure. And do I agree with you? I do. And Mr. Ott is actually at Maryland, not MIT. But
No. He wrote the paper with Themis Sapsis from MIT, where they introduced this valid prediction time, VPT. It's a metric that I actually use in my own research. So it's a paper with many authors. One of them is Ott, and the other one is Themis Sapsis.
okay, I guess I don't know that paper. But to say it again, if the underlying differential equation on whatever grid you choose is not chaotic, you should expect the predictions to be much more accurate. There's another ingredient here, which is I haven't yet told you how we determine the function phi, but let me take a moment to go back to the general statement, because that can also play a big role. Sorry. Here we go. How do we determine the function phi? Well, you need a representation of the function phi, and the representation that's been used in certainly most of the Maryland work takes this function and expands it in a polynomial representation. So it has a term linear in R with a matrix coefficient that is d by n. It has a term which is quadratic, which has a matrix coefficient which is n squared by d, and it could have a cubic coefficient which would be n cubed by d. That's not going to be a very successful representation if you want higher order terms in the polynomial. You also have no idea of the convergence of such a representation. We are now looking into representing this by a kernel density estimator, which should have a lot more information about the capability of this function phi to represent the input signal. But right now, we're using what's mostly published in the literature, and in our present work going on beyond that. So keep that in mind. I agree with your comments, George, but I think there's another subtlety to the one I just put here. All right. Now, driven dynamical systems, where you have, for example, I don't know, a dynamical system. The one I'm going to use is the one for the simplest Hodgkin-Huxley neuron in neuroscience, and I'm pretty sure I have a slide that shows what the equations are. It's a four-dimensional dynamical system of voltage and 3 gating variables, and it's driven by external currents. When you know the external current as a function of time, you can use that to both train the recurrent neural network, the reservoir, or and then if you don't know the current, if you think of it as a scalar function, which it typically is, which is projected from a higher dimensional space. And I'll give you a simple example of that. You should be able to represent that current in a form I'll now show you. Now, fundamental work was done on this 30 years ago by Norman Hunter, then at Los Alamos, and Martin Costagli, then at the Santa Fe Institute. Hunter's Los Alamos report was, as far as I can tell, never published, but Google will find it for you. And Costagli's work in some form or another appeared in Physica D around 1991 or so. So pardon my flippant comment here at the bottom. If you're living in a 24-hour news cycle, which is common these days, that work was 11,000 news cycles ago and just possibly got forgotten. But it's there, and I think these guys deserve the recognition. And here's the idea, that if you have a differential equation for the driving, the thing that you want to learn, then if you have a driving current that depends on dynamical variables of that driving differential equation, you can make a current that drives the system we're talking about with the variables of W, and then your differential equation for the data is a differential equation in U alone, plus some knowledge of the driving system. In other words, if you take this system altogether, it's an autonomous system, and then you can use the U that comes out of that to drive your reservoir. That isn't always true, but it'll be true in some of the examples I show you now. All right, I'm going to start with an example cooked up in kind of a neurobiological setting. This is the circuit of Hodgkin-Huxley neurons, 9 of them, with inhibitory connections from number 1 to number 4, inhibitory connections from number 8 to number 5, and excitatory connections elsewhere. And we take a stimulus that I will let you know now is taken from to be proportional to the X component of the original 1963 Lorentz system. So we know what the stimulus is, we know what the differential equation for it is, and so this is a test case for not a very large network of real neurons, but it's large enough. And here's what you get with the generalized synchronization from the auxiliary method. Now we're plotting the spectral radius versus not PNZ, but get the same result against the strength of the input signal. Again, blue here is the region of generalized synchronization, and red, well, the colors green, orange, and red are the regions of no generalized synchronization. Okay, we took that network. Here again is that picture shown in 3D. It's actually the logarithm of the distances between using the auxiliary method, reservoir A and reservoir B. And this is the region of generalized synchronization. This is the transition region that you were talking about, George. And here is the region of no generalized synchronization. So if you stay in this region for your choice of these parameters, the spectral radius and the strength of the input, you'll be down in here. And if you plot spectral radius versus the probability of non-zero connections, you get something that's rather similar, and the probability of non-zero connections, again, is a few percent. And here's the spectral radius. And what we're using here is that hyperbolic tangent reservoir. Okay, now I'm going to do something different. These are the Hodgkin-Huxley equations from 1950s on a basic neuron. These are also the ingredients for some rather more complicated neurons. This neuron belonged to the giant squid axon. And you see here, this is a sodium current with two variables that, if you taken together, give you the conductance as a function of voltage, because these gating variables, which are normalized to lie between 0 and 1, they represent kind of a probability for the opening of the channel through which sodium ions pass. This is the so-called reversal potential. It's the potential at which, if V equals this, the system is in equilibrium, and this potential is calculated by a standard thermodynamical formula that depends upon the concentration of sodium ions, in this case, inside the cell and outside the cell. This number is in the neighborhood of 50 millivolts. There's a second ion that is represented here, the potassium ion. The reversal potential for the potassium ion, because its concentration in the cell is generally much larger than outside, this is about minus 70 millivolts. These are familiar equations, as I said, postulated and tested by Hodgkin and Huxley in the, well, it must have been in the 1940s and 50s. The paper that won them the Nobel Prize for this was in 1952. This dynamical system is stimulated by an external current, and that's up to you. There are various reasons for selecting various of those currents. And the gating variables, which are this M, H, and N, all lie between 0 and 1, and all satisfy first order kinetics equation, in which alpha is generally increasing with voltage and represents the rate of excitation, and beta, which also these have dimensions 1 over time, represents the decay when the voltage gets very small. You may know all of that, and I don't mean to insult anybody, but I would like to explain it. Okay. All right. So the stimulus to the reservoir in this case consists of the 4 state variables of the Hodgkin-Huxley equation, plus the stimulation at time t, the stimulation at time t plus a lag, stimulation at time t minus 2 lags. This looks like, and is very close in spirit to, the formulation of time delay embedding in nonlinear dynamics that was introduced, well, I guess Dawkins did that in 1981, but this really is an instantiation of the ideas in the Hunter and Costagli paper. And so here's again the equations of the reservoir. There's some parameters in the reservoir, and we're going to find out that there exists such a function, although neither the conditionally up and off exponent nor the auxiliary method tells you about the function. You have to make an assumption about how it's represented. I talked about polynomial representations, which I think are simple, but have eventually limited ability. The coefficients just grow too fast. That cubic coefficient that I talked about has order of n cubed times d. If n is 1,000, we're talking about order of a billion or so coefficients that you have to determine by least squares method. And I guess you can do the computations, but clearly it's getting out of hand. Okay, so here's what we have. This is the 7-dimensional. That's 4 dimensions of the Hodgkin-Huxley equation, 3 dimensions of the Lorentz 1963 equations. This signal is chaotic, but it's statistically stationary when you're on the attractor, meaning that you can expect its future behavior to be known to you if you analyze the present behavior. That this is the input to a hyperbolic tangent reservoir. And here again are the generalized synchronization regions. And here again in the 2-dimensional contour plot are the regions without generalized synchronization. Here's the input strength versus spectral radius. Again, you can get similar plot for spectral radius versus probability of non-zero connections. At this point, you're probably getting the message that you learn about the same thing from all of these. Here's the 3-dimensional version of that. It's a little, well, not dissimilar, but it shows that there's a very steep transition between generalized synchronization and no generalized synchronization. And I guess if I had turned the 3D plot, you would see that this is in fact a very steep rise. So it's the 2D projection of that that was in the previous slide. So here, taking parameters that are inside the region of generalized synchronization, a spectral radius of about 0.9, strength of the input about 1.8 in some dimensionless units, the time constant in the reservoir equation of about 1/2 in whatever units you're using, and a probability of non-zero connections of 2%, and 1,000 dimensional reservoir. You train the reservoir by presenting the input for a certain amount of time, and then minimizing the difference between the input and the function of R, which you can represent as you will. And this is the prediction of that 9, oh no, this is just the Lorentz 63 in units of 0.02 milliseconds. So if you look at this, this is 10,000 times 0.02, which is 200 milliseconds, which is a kind of normal time scale. One could have extended for neuron activity, could have extended further if you want. And you can see that the prediction is remarkably good. If it were any better, you'd probably not believe me, but it eventually, it seems to differ from the data, which is here in black, and the prediction in the places where you have high curvature. So one of the suggestions that were made in improving these predictions probably can do better than what we've done here. Okay, I'm going to come back to what is really the suggestion of Hunter and Costagli. In the previous example, we took the X component of Lorentz 63 and with some magnitude or the strength of it, we know that it's a projection of the 3D signal of the XYZ state variables in the Lorentz 63 model. The effect of time delay coordinates, which I'm guessing you are all familiar with, is to unproject this projection by finding a different but equivalent space in which all of the characteristics of the attractor of the XYZ system are recaptured. And in general, if you have an I of t that is more complex than this proportionality to one of the dynamical variables of the Lorentz 1963 system, the idea is that you can take as many time delays, there are d sub I for input current, with time delays sub I, and you can determine d sub I and tau sub I from the usual methods of nonlinear dynamics. If you have a question about them, please ask, and I can tell you what's been used. So this is again a sketch. This is the idea that you unproject the current to get it into the phase space of appropriately large dimensions d sub I, and with a time delay. It's known for the Lorentz 63 model that the dimension happens to be 3. There are other examples where it's not. And the appropriate time constant is known in terms of whatever units the data is presented to you. The idea is you take this, you put that into a vector W, I called it, which consists of the original input and the time delayed input. And you do the same thing that I've described here, in which W becomes a function of the variables of the recurrent neural network, the reservoir. And again, you have all the same issues about this function phi, which we haven't tried to answer in detail. There was actually a paper by Ed Ott and Brian Hunt in around 1997 that attempted to answer this, but I think everybody agrees that there's lots of thinking and work to be done on what functions are allowed here. And here, just for the record, I point out to you that we did check that if you select the parameters of the adjacency matrix outside of the region where generalized synchronization holds, you get really bad forecasting. You can check for yourself. And in the paper I sent George, there's one example of that. Okay. This is where we take a deep breath and ask, why are we doing this? Does it make any sense to take a 3-dimensional or 100-dimensional system and represent it in a reservoir, recurrent neural network of 1,000 dimensions? It seems to be kind of like scratching your left ear with your right hand or something like that. But there's some good reasons. One is we can, and it's interesting to understand how reservoir computing actually works. The second, and in my opinion, more important, at least from a physics point of view, if not an applied math point of view, is that it's possible to implement a reservoir like the hyperbolic tangent reservoir in hardware. And that's been done by a group at Ohio State led by Dan Gauthier, who some of you may remember was at Duke for many years and did experiments in nonlinear dynamics. He moved to Ohio State a few years ago, and this paper in the journal Chaos details how he did this hardware implementation. And he showed that you can speed up the calculations of the underlying physics problem that generated the data by factors of 10 to the 2 to 10 to the 3. And I should have said not the scientific target, our scientific target is for now to take data on experimental data on biological networks, and I call them functional biological networks that actually do something. The network that we are examining is the network of the birdsong system, the avian brain system that controls the language that the birds use, which is vocalization for communication and protection against predators. And that's why we've chosen that circuit. The total number of neurons in the circuit we've chosen is the order of 500,000 to 1 million, which is significantly smaller than the circuits in the human brain, which can be 10 to the 9th to 10 to the 11th, depending on what size of the part of the brain you're interested in. And we thought that it was not wise to start there. So the fact that one can really speed up the calculations 100 to 1,000 times faster than the original calculations that went into constructing the data is an advantage that we are exploring. I think that's it. So let me unshare, and if you wish, I can go back to any questions you may have. Oh my gosh, it's almost 2 o'clock, 5 o'clock for you. I'm sorry. You're muted, George.
So I was just saying thank you very much, and do you have any questions from the audience?
Hi, this is Panos Tinis from PNNL. So I think I understand a little bit, but at the same time, I think I don't understand what is going on. So,
well, I'll take the blame for the things you don't understand. Okay.
No, I'll yes. So if you use what you had, the identical synchronization, right? If for the identical synchronization you use for the reservoir the system itself that you're trying to model, right? Is that the case?
You can do that.
Assuming that you know what the system is, of course, but you want to apply it to cases where you don't know what the system dynamics are, right?
Well, we've done what I call twin experiments,
okay,
which are simulations and not experimental data.
Right.
In the applications that we envision, you do experiments on the system of interest.
Yes.
And you take those data, and that becomes your input.
Yep.
U of t.
Yes.
The reservoir learns that input through the relationship of U equals what I called phi of r.
Right.
And then it becomes an autonomous differential equation that you can solve very fast if what's at the nodes of the reservoir are simple, like sigmoids, hyperbolic tangents. And that's what the group at Ohio State implemented to show the numbers that I discussed.
Right. So if the way I understand it, in order for this phi to exist, or at least to be easy to train for it, it would help if the input is close to r, right? Because if they're identical, then phi is the identity, right? If u is equal to r, phi would be the identity.
Absolutely correct.
Right. So,
that isn't necessary. I mean, I've shown you examples where the dimension of U is a few percent of the dimension of the reservoir, or in the case of the shallow water equations, 10%, or
right,
20%. Okay, but
okay, yes. So, so my question, I don't know, or my confusion is, what condition? I mean, all I'm saying is that if you use a random reservoir, right, then the burden of learning this mapping from R to U falls on phi. So the further away the random reservoir is from the actual dynamics of the system, the more complicated this function phi must be so that it can take you from the reservoir to U, right? From R to U.
That appears not to be the case.
It's not?
No.
Okay.
The function phi that was used in the work that I presented and in the work of the Maryland group and other groups is a polynomial expansion. Phi equals some numerical coefficient times r. That's that simple. It's linear.
That's simple. Okay.
I think it's embarrassingly simple because I think it doesn't capture what happens in more complicated reservoirs, but I haven't shown that or have a proof for it. But it's that simple. And the fact that the dimensions are distinct, d-dimensional input, n-dimensional reservoir, would argue that anything can be in the reservoir, and the dimensions don't necessarily be as high as we used, but that's what we chose.
Yeah, I agree that anything could be in the reservoir. I just thought that, the closer the reservoir is to the actual dynamics of the input, that would help phi to be simpler. So but you're saying that it's not necessarily something that you have. So where is the catch here? Where is the magic?
Well, I'm hoping that there is no catch. And the
Right.
reason I talked about generalized synchronization and it's having been observed in many physical systems is, at least for physicists like me, the kind of demonstration that you need, that's the crucial ingredient. And for identifying when you can get generalized synchronization, it does not tell you what the function phi is, but simple ones, and I'm hoping more complex ones, as I suggested, coming from kernel density estimation, which is a better representation of a distribution in state space, will work.
Okay.
Really, so it seems simple, but some of the steps, in particular the representation of phi, since we have no general principles for it,
Right.
I would say it's really important to dig out what kind of phi, what limits on phi there are. None are known at the moment.
Okay.
So your question is really a great one, but right now, question's up in the air. I mean,
Right.
well, or it's in the bucket if it's a reservoir. All right.
All right. Well, thank you.
Of course. Thank you for the question.
Any other questions?
I have a question, and the answer might be really quick.
Go ahead, Andrew.
Okay. I was wondering if you've tried this reservoir computing technique in the presence of like multiple attractors or something like that. Because there's these classic kind of like shallow water things where if you set it up in a certain way and you get like solutions that look very different just based on like, a different physical context.
We haven't done that, but I can give you my guess. And that is when you have multiple attractors, what you have is multiple basins of attraction, typically with a boundary that's fractal between those basins of attraction. And that so far what we have done is take a solution, for example, for the shallow water equations that could be refined by a more refined grid, and said that's what we're going to forecast. If you have multiple basins of attraction, I think you could extend the method to having a different phi relationship in different basins of attraction. And that would not be too hard if you had data from experiment or from theoretic or numerical models that showed those multiple attractors. I don't see any reason it would not work if you informed the reservoir of what was going on. The reservoir doesn't know anything about shallow water equations, about neurobiology. Well, it doesn't know anything about anything. You have to teach it.
Okay.
So let me leave that as a challenge to you, and thank you for the question.
Yeah. Any more questions? I'll give them a minute to think about it, but how about representing phi with a neural network? It could be very expressive. We can make it deep. We can make it any way we want. I was thinking actually to use a GAN, a generalized adversarial network, to capture a very difficult phi. Why not?
Why not? I agree. The reason I chose kernel density estimates is that they're widely explored.
Yeah, I know, but whatever you can do with that, you can do better with GANs and stuff, and other neural networks. So I'll try to beat you to that.
You're welcome to, or you can even join me.
Wow, that would be something. I mean, that's the idea, sort of. But it may be very formidable. Also, I have this question about, because you advertised this in the beginning as a doing for weather forecasting. That doesn't look very scalable to me. I mean, taking like the shallow water equation and so on. Even for a regional climate model and so on, or whatever region, that looks to me very, very expensive to scale it to.
Yeah. So I agree with you, and here are the numbers that absolutely, totally convince me you're right. If you look at the models that the European Center for Medium Range Weather Forecasting, the one in Reading, the number of degrees of freedom in their GCMs as of the last time I checked, so it's probably more now, was 15 billion. Okay. And the number of measurements that they have is in the order of 1% of that. That's 100 million of measurements from satellites, from ground stations, from ships at sea. I mean, it's an amazing, amazing achievement, but it's a real challenge.
Yeah.
So that's another reason why I thought that in neurobiology, where the dimensions of the dynamical systems can be 10 to the 5th to 10 to the 6th, we might achieve more, both scientifically and analytically as we understand it. It's my guess. All right. Do I have the resources of ECMWF? No.
Yeah. Okay. Any more questions for Henry?
Thank you all for your time. I know it's late in the afternoon for you, but since we're having a horrible winter weather, 75 degrees Fahrenheit outside, I think I'll take a little break.
That's right. Thank you very much, Henry. Thanks for stopping by today, and I'll share the paper with everyone. Thanks.
Oh, it's the book even.
Yes, and even the book. Yes, you have to tell me. Yes,
oh,
thank
the paper. Yes, for sure. That
yeah.
You're more than welcome to.
The archive. Yeah. Okay.
Take
care, everyone.
Thank you again. Bye-bye.
Bye. Thanks.
Thank you. Bye.